So we've talked about how we know that it is not natural cycles. We've talked about how we know that it is not the sun. It is not orbital cycles. It is not volcanoes or geologic activity. But how do we actually know that the current change that we're seeing in our climate today is due to humans? Well, the story actually begins back in the 1800s. In the early 1800s, a French mathematician and scientist called Joseph Fourier, if you've taken any math classes, you've probably heard his name before. Joseph Fourier went to Egypt with Napoleon. He was French. And in Egypt, he became interested in, well, why do people wear white clothes versus dark clothes? And why am I so much hotter in my dark coat than those people are in their white clothes? So he started thinking about heat, and he started doing some calculations. And what he found out is that according to his calculations of reflectivity, how much energy we're getting from the sun, and what our temperature is and how much energy we're giving back off to keep in balance, according to that, the planet should be much colder than it is today. Almost 60 degrees Fahrenheit colder than it is today. In fact, the planet should be a frozen ball of ice. But it isn't. So why is that? He speculated it was because of the presence of our atmosphere. So just like a blanket traps your body heat and keeps you warmer than you would be otherwise, in the same way he speculated, our atmosphere acts as a blanket, trapping some of the Earth's heat inside the climate system and not letting it escape to space. So he called this the greenhouse effect. Now, unfortunately, it doesn't actually work the same way that a greenhouse works, so it's a bit of a misnomer, but the name stuck. I would prefer to maybe call it the blanket effect because it does work that way. It works by the fact that our atmosphere has trace gases in it. Now, most of our atmosphere we know is actually nitrogen, 78%, and about 21% is oxygen. And then we've got a lot of little tiny gases we don't think about very much, but it turns out that those are the ones that are responsible for this blanket effect. But which gases were they? Well, we had to wait another few decades until an Irish scientist called John Tyndall came along. John Tyndall was in a field called spectroscopy, where you measure the vibrational and rotational wavelengths of molecules. I know you're thinking I didn't sign up for a chemistry class. Don't worry, we won't get too far into that. But he was able to identify the signature of different molecules depending on which wavelengths they vibrated or rotated at, which determines which wavelengths of energy they would absorb and re-emit. What he found is that water vapor and carbon dioxide and methane would absorb and re-emit radiation in the infrared wavelength right in the middle of the band of energy that the Earth gives off. So bear with me a little bit here. We're going to look at this figure that looks a little bit technical, but let me explain it to you. This is something that shows how the sun's energy, because the sun is 57,000 degrees, the sun's energy is much shorter wavelength, it's higher energy, it's primarily in the visible spectrum. The sun's energy shines down and heats the Earth, and the Earth heats up and gives off heat. But the Earth is only about 57 degrees Fahrenheit, it's not 5,700 degrees Kelvin. So because the Earth is a lot cooler, it gives off a lot longer wavelength energy, which is in the infrared spectrum. So it turns out that what Tyndall found is that there's specific gases that absorb the Earth's energy. So the sun's energy goes almost right through like a window, and then the Earth heats up and gives off heat energy, and then that heat energy is absorbed by these molecules, but it's not kept by them. It's absorbed and re-emitted. So then you might say, well, if it's re-emitted, then how does it warm the planet? Well, the energy is coming from the bottom up, right, from the Earth's surface. And so the energy goes up and it hits a molecule of carbon dioxide, and the molecule absorbs that energy. And then the molecule re-radiates it equally in all directions. So half the energy is now going back down and half is going up. So it's effectively cut it in half. And then if the half that's going up, it might hit another carbon dioxide molecule or methane or water vapor. It absorbs it and re-emits it. And you've got half of that going down, half of that going up. So now you've only got 25% going up. So that's how these gases trap heat. Now, John Tyndall wasn't done. He also connected the dots between coal mining and these gases, because he knew that when you mine coal, it releases gas that's been trapped between the layers of coal, which actually is methane. That's the reason why they had canaries down in the mine, literally, because canaries are very, unfortunately, sensitive to methane. So he connected mining directly to these trace gases. So in other words, he knew in 1850s that human activities were affecting levels of these heat-trapping gases that wrap an extra blanket around the planet. Now, at the same time, on the opposite side of the world, there was this woman called Eunice Foote. Eunice Foote was an amateur scientist. She didn't have all the experience and the education and the scientific equipment that Tyndall had, but she did have her brilliant mind. And so she devised an experiment using glass jars in her backyard that she filled with different types of gases and put out in the sun to see which ones heated up the most when exposed to sunlight. Now, there's a bit of a flaw with her experimental design. And if you're following along, you might have already caught it. Because these heat-trapping gases operate where? In the infrared or heat energy part of the spectrum. And if she put them out in the sun, what was she doing? She was primarily trapping the sun's energy, although there would also be energy coming up from the earth. So she didn't quite isolate the effect of these gases on the infrared radiation the way that Tyndall did. But what she did was amazing. In the paper that she published in 1856, that was read at the American Association for the Advancement of Science's annual meeting, which is still happening today, which I present at myself. In that paper in 1856, she actually speculated that if the Earth had more carbon dioxide in its atmosphere, it would be warmer. And today we know that that absolutely happens, because it turns out that Venus, which has a huge amount of carbon dioxide in its atmosphere is actually over 90% carbon dioxide. Venus should be minus 46 degrees Celsius, but it is not. It is instead plus 400 degrees Celsius. Why? Because of the carbon dioxide in its atmosphere. So how does this connect to humans? Well, by digging up and burning coal and natural gas and oil eventually too, we are putting more and more carbon into the atmosphere. We know how much because we can actually measure it. What happens when we're increasing the levels of naturally occurring heat-trapping gases in the atmosphere? It is as if we are wrapping an extra blanket around the Earth. And just like you would if somebody snuck into your room at night and put an extra blanket on you that you didn't need, just like you would heat up and start to sweat, in the same way the Earth is heating up because we're wrapping this extra blanket around it that it does not need. Where is this extra blanket coming from? Well, about 65% of it is carbon dioxide, CO2, and then about 18% of it is methane, CH4, and then we've got other gases like nitrous oxide and even some of the same substances that deplete the ozone level that make up the rest. What different economic sectors do they come from? Well, when we look at this data, it's very clear this is a widespread issue. We've got about a quarter of it from electricity and heat production, about 20% of it from transportation, about 25% from agriculture, deforestation, and land use change. We've got fossil fuels and burning trees all throughout our system. And that's why it's such a huge issue to fix. Now, how much warmer are we going to get? That depends on us because we are the ones who are wrapping the extra blanket around the planet. But with the physics that they knew in the 1800s, a Swedish chemist called Svante Arrhenius, who is actually a distant relative of Greta Thunberg, true story, he was able to calculate in the 1890s how much the planet would warm if we doubled or tripled levels of CO2 in the atmosphere. Now, he thought it would take a few thousand years for that to happen because he didn't realize that our carbon emissions were exponential. He thought they were just linear. But the numbers he calculated, and even the numbers he calculated for how much faster the Arctic would warm than the rest of the world, which we know is happening, those numbers are astonishingly accurate compared to the most up-to-date and sophisticated climate models we have today. And he ran those numbers by hand in the 1890s. It took him 2 years of handwritten calculations, but he did it. So, in summary, what's the greenhouse effect? The greenhouse effect is the trapping of the sun's energy in the lower atmosphere by naturally occurring greenhouse gases that are mostly transparent to visible energy from the sun, but that are very opaque to infrared or heat energy produced by the Earth. What is the enhanced or artificial greenhouse effect? That one is us. That's the fact that we are wrapping an extra blanket around the planet, which causes it to trap even more heat than it would otherwise. But then we've got one more, and that's, well, what's global warming? Global warming is the symptom. It is the rise in the temperature of the planet as a result of this extra blanket that we're wrapping around it. And if you remember back a couple of lessons, we also talked about how Guy Callendar, a British engineer, was the very first person to actually ride around the world, collect weather station observations, and calculate and show that the planet was indeed warming. We can use these climate models even to create imaginary planets we can experiment on. And this is a great tool from Bloomberg, actually, called What's Warming the World. I want you to watch this video with me now. So this animation, first of all, shows what's really happening. This is our observed global temperature, the black line. But then with climate models, we can build other planets. Planets where we say, well, what happens if the Earth's orbit is the only thing that's affecting temperature? If it was the Earth's orbit, we'd be gradually getting cooler. What happens if it's the sun? If it's the sun, we would also be getting a tiny little bit cooler, but not much. What happens if it's volcanoes? We'd see some big dips when we had volcanic activity, but overall not much change. What happens if it's ozone pollution? That is a factor that affects our temperature, but it warms us only a little bit. It really is greenhouse or heat trapping gases. That is the only reason why the planet is warming. And when you put together human and natural factors together into one figure, as you can see here, what we see is that it is us. We can do the same type of experiment on every single continent around the world. Here, the black lines are the observed temperature. The blue is the range that the temperature would be in naturally, and the pink is the range that it would be in with both natural and human factors acting together. As you can see on every single continent of the world, in the last 50 years, the black line clearly falls into the pink area. Now, some people would say, oh, so you're saying there's no natural factors at all? Of course not. They affect us too. It's kind of like saying, well, was your heart attack genetics or was it poor lifestyle choices? In some cases, you can say, well, it was mostly poor lifestyle choices with perhaps a little bit of bad luck in the genetic pool. And that's sort of what we can say here. In fact, we can actually say we have a bit of good luck in the genetic pool, so to speak, because according to natural factors, we should be getting cooler, not warmer. So they're helping us out a little bit, but instead we're getting warmer faster and faster. And then people might say, but aren't scientists still arguing about this? Isn't the jury still out? And the answer to that is no. Let me give you two quotes. Listen very carefully to these two quotes. Ready? Warming of the climate system is evident from observations. Most of the increase is very likely due to the observed increase in heat-trapping gas concentrations due to human activities, including burning fossil fuels. Second quote. Climate change is being brought about by human-induced increases in the concentration of atmospheric carbon dioxide, primarily through processes of burning fossil fuels. These two statements say pretty much the same thing. Statement number one is the conclusion from the Intergovernmental Panel on Climate Change in 2007, and statement number two is from Guy Callendar's paper in 1938. So no, scientists are not still arguing. We have checked every natural factor, even unknown ones. We know it is not natural today, it is us. And for more than 160 years, we have known that trace gases in the atmosphere control the thermostat of the planet. We have known that burning coal and gas and oil produces more of these heat-trapping gases. We know that that is the primary reason why the planet is warming today, and for that reason, we know that the future is in our hands. The bottom line is this. We have known for more than 160 years that climate change is real and it's human-caused.